Welcome to the next installment of our medicinal chemistry journey on autonomic nervous system. This time, we will talk about adrenergic agonist drugs. Our adrenergic agonist drugs have this parent structure called beta-phenylethylamine. Our beta-phenylethylamine is named according to the components of its structure. First, the phenyl ring with 1,2-dihydroxy substitution, and then followed by the ethyl bridge, which contains our carbon 1 and carbon 2, and hydroxyl substitution, and the R2. The next one is the tail part, which is called as the amine, with the R1 substituent. So these structure are the ones being manipulated to change the functionalities of our adrenergic drugs. So manipulation or substitution on these different parts is categorized into three chunks. First, the first chunk is on the amine tail with the R1 or alkyl substitution, followed by the ethyl bridge, which has R2 and another slot for alkyl substitution. And the third one, the third chunk, followed by our beta-phenyl ring, which is very important in our adrenergic drug action, especially for adrenergic agonism. In order for a drug to act as adrenergic agonist or to become a direct acting sympathomimetic agent, it should have the following attachments. So it should have maximal activity when our hydroxyls are attached to the beta carbon and to our phenyl ring. So example for this drug are norepinephrine, epinephrine, and isoproterenol. Moving forward to the first chunk of our beta-phenylethylamine structure, which is the amine with the R1 or the amine with the R position ready for substitution. This position or this area can be modified and can produce different functions or can produce different therapeutic actions. So, just some background, our amine has a pKa approximately 8.5 to 10, which makes our amine basic and positively charged. So, if our amine with R1 available for substitution will be substituted with an alkyl, you remember that as the alkyl size increases or the more carbon atom attaches in our R1, the more it will have a selectivity for beta receptor and it will have less activity with our alpha receptor. So increasing number of carbon in our R1 favors selectivity for beta receptor. So alpha and beta receptor activity is maximum only when R1 or in our first area for substitution, it only contains one carbon or the methyl substituent only. For example, epinephrine. Now for R1, which is substituted with isopropyl instead of methyl, it will have it will have negligible alpha activity and it will become more specific with beta activity. So isopropyl is a bulk alkyl and bulky alkyl favors beta receptor activity. Now for your activity on this part, look for the adrenergic drug that contains isopropyl on its R1 position and is useful as beta receptor agonist. Moving forward, if our R1 also is substituted with a more bulky substituent such as tert-butyl, it will have affinity with alpha 1 receptor, but there is no activity at all. Instead, it will have beta receptor activity. Specifically, if tert-butyl is the one being substituted, if tert-butyl is the one that substitutes our R1, it will produce beta 2 selectivity. Now, I want you to look for the structure of terbutaline and albuterol and look for the R1 position if it does contain tert-butyl group. The next substitution we can do in our R1 is to attach an aryl alkyl group. So aryl alkyl group is a combination of a straight chain and a cyclic or aromatic group, and if it ranges from 2 to 11 carbons or 2 to 11 carbon chain, it will produce, of course, beta selectivity. And again, it will have an increased lipophilicity because aryl and alkyl are lipophilic, and the more you increase the number of carbon or the chain, the more it will become lipophilic. Therefore, if R1 is replaced by those kinds of substituent, it can produce a drug that has better cell penetration and have longer duration of action. So I want you to compare and look for the structure for salmeterol and formoterol, which are beta selective, and identify which among them has more longer duration of action and has more selectivity with specific receptor. So R1 substitution on the amino nitrogen can determine alpha or beta receptor selectivity, as I have mentioned in the previous slide. So remember that this amine here should be only limited to primary and secondary amine to maintain its adrenergic activity. Tertiary amine and quaternary ammonium salts do not favor our adrenergic activity. And as the size of the nitrogen substituent increases, alpha receptor agonist activity decreases. So it favors now, the affinity favors with our beta receptors. So it can have an activity or an action on our beta receptor. So these are the different structures of drugs that I want you to look at and compare. So all of them contains an amine that is primary or secondary in secondary degree in branching. So these are qualifiers for our adrenergic drugs. Now look at the R1 substituent. So the minimum requirement to have an adrenergic activity is to have a substitution in our R1. So norepinephrine, it has no substituent or no substitution, but it can still, or it is the prototype of our adrenergic agonist drug. Now epinephrine, it contains the methyl, which is favorable to produce maximal activity for both alpha and beta receptor. Now, as I've mentioned, if our R1 increases or if it contains branching or it contains aromatic, it favors beta receptor. So it depends now. If contains aromatic, it favors beta receptor, and specifically it will become beta 2 selective.